we're going to start with an introduction of the finite element method. And to do so, we will introduce what's known as the direct stiffness method. The direct stiffness method is the basis for most commercial and free finite element software. So this is what's going on under the hood. And so we're going to go through it in kind of painful detail, or let's say tedious detail as we start to really understand how you take a structure, discretize it, solve for forces and displacements at all the nodes where you've discretized this structure, and assemble everything all back together, and determine what, say, the displacements are and the forces and therefore stresses are in this structure as it's loaded. We're going to do this in the most simple way as possible. We're going to use, we're used to thinking about trusses, right? We think back to statics and even some work we've done in this class where you have some truss that is pin connected and you're going to apply some load somewhere and see how this truss deforms or see if this truss is stable, so on and so forth. And you can really translate that idea of thinking about trusses into how we apply the finite element method. Because really what we're doing is we're going to take a continuous structure and we're going to discretize it into n number of nodes. Those are kind of our pins, connecting various elements that are going to make up this continuous structure. Now, when you hear about terms like mesh refinement, when you're using something like SolidWorks or Creo or Abacus or ANSYS, what you're talking about is kind of putting in more and more nodes and putting in more elements in between those nodes to be able to have a finer and finer resolution of the structure you're solving for. Typically, what we're going to do is we're going to kind of use a very simple structure that has a very simple mesh. It's really just we're going to start with a truss. But these ideas of how you kind of discretize a structure, there are entire areas of kind of computational mechanics that you can study and learn about to kind of understand this process a bit better. We're going to start with as simple as possible. We're going to start with something that's a truss, and we're going to use the simplest possible element. So the properties of the thing connecting the two nodes. And the simplest possible element is going to be what's referred to as a two-node bar. I'll go through this in a second. So it's basically a spring, a linear spring. You pull on it, it's got some force displacement response that's similar to springs. The idea here is we're going to illustrate, let's see here. The idea here is that we can, using some basic steps, now they're kind of tedious, but some basic steps with a simple structure, we can illustrate the direct stiffness method. So let me just draw out a little bit of what we're saying here. We want to be able to model a typical pin jointed plane or truss. So we might have something that's something that's maybe as complicated as this, where we have various, I'll describe what I'm drawing just in a moment. So here's a simple pin connected truss, where at each connection here we have a pin. And to translate this language I'm using in kind of statics into something that you would see in typical kind of direct stiffness method finite element language, this is a member, and a member is connected between two joints. So these two things here are our joints. And this is, well, I guess I should be drawing that, really pointing down here, is a support. So for a really simple structure, and this one's I would not say is really simple, for a really simple structure, we can do these computations entirely by hand if you're using a simple two-node bar element connecting these joints together. And the purpose of us doing this by hand is to kind of show you what's happening underneath the hood in a typical finite element code. This will be a way to kind of illustrate what the solution method is doing, how when you click go on SolidWorks, it's able to actually solve for you and show you what the stresses are or displacements are in your structure that you've loaded. So the purpose, for this class is not to make you proficient in any particular finite element software. The purpose is to show you mathematically what these finite element codes, commercial, which are usually a black box and you have no idea what's happening, or some open source ones, are actually doing under the hood. And there's three basic steps that we're going to follow here. And the procedure looks like this. First, we're going to idealize the structure. Now, for a truss, in a lot of ways, a truss is already idealized. You already are looking at a structure that is a bunch of bars connected by a bunch of joints. But you could imagine thinking about a more complicated object like a lamp or your computer monitor, where you're going to say, okay, how do I idealize this structure into something? And this is where you're really talking about kind of meshing this, discretizing that continuous structure into a bunch of nodes connecting different members together. So in a lot of ways, this first step is kind of done for us, but it's going to be helpful to introduce some of the terminology and some of the mathematical nomenclature as we idealize the structure. And then the second step is what's referred to as breaking it down. And what that means is we're going to take this structure and we're going to split it apart into individual elements and solve for what's happening on each of these elements. And then we're going to reassemble the whole structure. Once we've done everything individually, assemble it all back together to show you what the deformation or forces and stresses are in the actual structure that you're interested in. So idealizing the structure is where we're going to start. And like I said, this means we're going to replace a physical structure with a mathematical model. We're going to have to make some approximations in here. So anytime you're doing some sort of a mathematical model, you're going to have to introduce some approximations. For the sake of this very basic introduction to the direct stiffness method, a couple of the approximations we're going to make are that the members only carry axial loads and that the connections are all frictionless. There's various other assumptions we're making in this process, but this just gives you an idea. And these are by no means any limitations of the direct stiffness method. This is just what we're doing right now to simplify our mathematical model. Once we finish this for the simplest case, we'll go back and relax this first assumption about only carrying axial loads. We'll change that to something where you can have a structure that can have axial deformation and bending deformations. You can add friction, you can add whatever physics you want to the model. It just kind of increases the complexity of it. So to start with, we're going to look at what is generally thought of as the simplest plane truss. Plane truss meaning this truss only exists in the plane. And I'll draw that over here. So the simplest plane truss is going to be this right triangle. And I'm going to be very explicit about labeling some of this, and this is going to come and become important as we go forward. I'm going to put the origin of the coordinate system in the at the lower left-hand part of this structure. So I'm going to put, here will be the x direction, here will be the y direction. And what will become important later is that this is going to be what's referred to as, so x and y are the global coordinate system. So that means this is the coordinate system of the structure. This is the coordinate system that we describe where the structure lives. Okay. We're going to do some additional labeling here. We're going to label all of the nodes, which are going to be at the joints of this structure. And we'll start labeling over here. Let's go. So we'll call this thing 1, this one 2, and up here we'll label this as 3. And in addition to labeling the nodes with numbers, we're also going to label the members, except the difference is we're going to label the members within parentheses. So we'll call the member between 1 and 2, member 1. Between 2 and 3, we'll call this one member 2. And between 1 and 3, we'll call that one member 3. These members, it's easy to conceptualize them as a truss. We know that these members will have some sort of geometric and material properties. What does that mean? It means that in the most general sense, oops, there we go, sorry. In the most general sense, each of these members could have its own elastic modulus. So we could write that as E1, E2, E3. Pretty clearly, each of these ones will have their own length. So length 1, length 2, length 3. And we could also imagine them having their own, for instance, cross-sectional area. As we add more physics, so if we allow for bending, then these structures would have their own second moment of area. If we allow for shearing, these structures will have their own shear modulus, and so on and so forth. We're going to write this. We're going to kind of, for simplicity of notation, we're going to write this in general by dropping the parentheses, and we'll write this as E to the little e, L to the little e, and A to the little e. It's important to note that these are not being raised to a power. They're just denoting kind of a placeholder for which element are you talking about and which properties. And I denoted the joints in orange. So that little e just means a generic member, so we won't specify it at the moment. So one thing you might recall for back to statics with a pin jointed truss. So this will be, I'll just specify that. I've already written it once, I think. So a pin jointed truss can externally applied forces and reactions can only act at the joints. So let me write that down. So this is something you might recall from statics, doing a static analysis of a truss. The forces and reactions are going to only act at the joints. This will be true when we move to higher, more complicated physics. So for instance, if we allow for bending of the structure, then any applied couples or moments will only be allowed to act at the joints. So what this means is, because of this fact, what this means is we're going to analyze forces and displacements at the joints. So we have a pin jointed truss. We're going to do something to it. So maybe we're going to poke on the node number 3, and we want to know how this truss is going to deform. And so what we'd like to do is analyze the forces and displacements at each of these joints. So we're going to need the axial components of these forces. We need the axial components of these forces at each joint. So I need the axial components of the forces, which means I need to calculate F in the x direction and F in the y direction. But I need to do that for every joint. So in reality, what I need is, I'm going to move this over. I need to calculate F of x at joint I, and I need F of y at joint I. Now we have a planar truss here. We only have everything in the x and y plane. So at each node, there are going to be 2 degrees of freedom, right? We can have just displacements in the x and y direction. And so we could write the force vector. This force vector is going to be a column vector. So let me see if I can write this out here. So we'll be able to capture all these in a column vector F. So we have 3 nodes, and there's 2 degrees of freedom. So this column vector should have 6 entries. So we would expect it to have F of x for the first node, F of y for the first node, F of x for the second node, F of y for the second node, and then again F of x for the third node, and F of y for the third node. And then we can, oops, I don't want to do that. I want to, this is our force vector F. This is a column vector. Okay, so those are what our forces are doing. Now we can think about our displacements. So let me see if I can. So our displacements are completely defined by the displacements of the joints. So let me write this out. So the displacements of the truss are completely defined by the displacements of the joints. And so the same thing is going to be true. So then we're going to have, there's 2 degrees of freedom. So we're going to expect there to be a ux and a uy, where I'm using the lowercase u to denote the displacements. And again, we need to calculate these 2 displacements, in this particular case, for all 3 of the joints, or all 3 of the nodes. So we're going to say at each node, so we're going to have uxi, uyI, and therefore, let me write this out over here. This is all got garbled here, didn't it? There we go. That's a little bit better. Okay. And so we can do the same thing as we did before. And our displacement vector is going to look basically the same. So we would have ux1, uy1, ux2, uy2, ux3, and uy3. Again, we have a column vector for our displacements. These are the state variables of our problem. There's a little bit of an aside here. If you're doing, and we'll come back to this once we actually start to solve the problem, but I want to bring this point up now. And typical, let's see here. Let's talk just briefly about boundary mechanics. Sorry, boundary conditions. And in analytical mechanics, so say if you're going to sit down and solve an equation exactly, you're going to write down the partial differential equations that you would like to solve, and you know some particular boundary conditions. In analytical mechanics, it's essential for those boundary conditions to be baked in right at the beginning of formulating the problem. Like they can't really be separated. You have to be considering the boundary conditions when you're considering the governing equations. So the boundary conditions are kind of, if you want to say, they're baked in at the beginning. Whereas in computational mechanics, we typically only consider them at the end. At the end of this problem, once we formulated everything, we can go in and set specific restrictions on, say, displacements or rotations at various nodes. So this is something that is really only considered at the end during problem solving time. Okay, so displacements of the truss are defined by displacements of the joints. We know that externally applied forces and reactions can only act at the joints. So if we know the forces at the joints, we can solve for the displacements at the joints, but there's going to be some sort of thing connecting these. And if you recall from just a simple spring, you typically have the force is equal to some stiffness, K, times the displacement. So let me write this out just as a reminder, because that's basically what we're going to be doing. So recall how springs work. So the force is equal to some stiffness times some displacement. And that's exactly what we're going to find here. So we are going to have that our force, which is a vector, is going to be equal to our displacements, which is a vector, and our stiffness connecting these two will have to be a tensor. So in this particular case, we're going to have some matrix or tensor connecting the force to the displacement. Our force vector for this structure is a 1/6 vector. Our displacement vector is a 1/6 vector. So for this structure, our stiffness matrix will be a 6/6 matrix. So we're going to relate F to U. We're going to assume that our truss behavior is linear, so that all the equations that are connecting these two vectors, the force vector and the displacement vector, we're going to assume that those equations are linear. And we're going to assume that if all the displacements vanish, so if there's no displacements of the structure, then all the forces vanish. So I'm going to just remind us here. So this is a 1/6. This is a 1/6. And this will be a, so let me write this out here. 1/6 vector. 1/6 vector. 6/6 matrix. The stiffness matrix is kind of awful to write out in symbolic form, but I'll show you a little bit of how it'll look just to give you a sense. So for instance, you would expect there to be some sort of connection between the force at x1 and the displacement at x1, and some sort of connection between the force at x1 and the displacement at y1. And we can keep going here. And then you can imagine there being the force at y1 and the displacement at y1, and so on and so forth. So you can fill this out until you get a 6/6 matrix. And this matrix has a particular name. It's what's known as the master stiffness matrix. And there's 2 points about it. This matrix is symmetric. And these entries are stiffness coefficients. And these stiffness coefficients have a very physical interpretation. I'm going to write this out. Entries are stiffness coefficients. And these have a physical interpretation. So what that means is inside this matrix is what dictates how much the structure resists the forces or moments being applied. So in the case of a planar truss, where we only have axially loaded members, and we are applying forces at these nodes, then our stiffness matrix is going to be made up of things that resist stretching or compression. So it's going to consist of things like the elastic modulus, the cross-sectional area, and the length of the rod. As our physics gets more complicated, so if we, for instance, we're going to allow bending in addition to stretching. Then our stiffness matrix would include all the axial rigidity, so E, A, and L, but it's also going to include the bending rigidity terms. These are the things that are typically going outside of when you multiply all of the components of the strain energy, things like the modulus, the second moment of area, I, and the length. And then you can imagine this for any physics that you can cook up, all of the resistance to deformation is going to go inside this stiffness matrix. How stiff is this structure to the various types of displacements being applied? Okay. So this is what we mean by idealizing the structure. But right now we have no idea what is this stiffness matrix. And in a lot of ways, that's our goal, is calculating the stiffness matrix for the structure. Once we have that, then it's just a matter of solving F equals KU. That's it. And it's just, the problem is that F equals KU, you can imagine, here we have the simplest structure. You have a 1/6 vector equaling a 6/6 matrix times a 1/6 vector. As you make your physics more complicated, as you have more and more nodes, this matrix increases in size significantly. And the goal for us right now is to figure out what goes into this stiffness matrix for the particular problem that we're solving. Okay. And that leads us to step 2 for this. And step 2 is referred to as breakdown, where we're going to disconnect or disassemble the structure. Okay. Questions before I continue on? Nothing? Okay. So here is our truss, and right now it's in its structure form. It's a structure. It exists in the global coordinate system, which is telling you where all the components of the structure are in space. And what we want to do is split this structure up into its individual components. What does that mean? We want to take this structure and we want to kind of blow it apart, disconnect the joints, disconnect the nodes. So for instance, element 1 can exist independent of element 2, and the same for element or member 3. And now when we do this disassembly, one of the key things that we're going to do, and this is where a point of confusion can come in, so focus on this briefly and it'll help everything that comes forward. One of the things we're going to do when we disassemble this is that we're going to now evaluate each member individually And here's the crucial point. We're going to evaluate each member in their own coordinate system. So for the first member, that's a fairly trivial remark. Because the coordinate system of this first member will coincide with the coordinate system of the global structure.
So we forget about the supports.
For the moment.
Okay.
For the moment, we forget about the supports. That's where this remark about these boundary conditions comes in, because the supports are really telling you, how am I restricting displacements, or in more complicated terms, displacements and slopes? How am I restricting displacements of this structure? When you go to, once we have the stiffness matrix, that in every entry of K in that 6x6 matrix there, once we have that and we're ready to solve the problem, we're going to impose some force, and we're going to say at node 3 have a force of some value, and then we're going to have to tell it that in order to solve this equation, we're going to restrict the degrees of freedom. We're going to restrict the motion of node 1, so we're not going to let node 1 move in the y direction or the x direction, and we're not going to let mode 2 move in the y direction, but we will let it move in the x direction. But that comes later. That comes at the point where we solve it. For right now, we can just ignore them.
Okay, thank you.
So we've disassembled this structure, and now we have to assign a new coordinate system for each one. So for instance, the first one's pretty trivial. We're going to assign the coordinate system such that the x-axis runs along the long axis of the member. So here, and we're going to call this, I'm going to zoom in. Whoa, okay. Sorry. I'm going to zoom in. Let's try that again. We're going to do two things to denote these new coordinate systems. One is we're going to now refer to them as x and y bar. And this is to make it extra clear that we're referring to the local coordinate system of each element or of each member. And in addition to labeling these coordinates with a bar, we're also going to label them in terms of what member are they referring to. So this is x bar 1, y bar 1. Let's go up here. So here we're gonna have x bar 2, y bar 2. It's probably annoying to read that sideways, isn't it? Hold on. We'll do that again. X bar 2, y bar 2. And now over here, we're going to have x bar 3, y bar 3. And so now I want to make it clear that I'm referring to our local coordinate system. And we'll write this as x bar of a generic element, y bar of a generic element. Okay. Now again, we can think about how this individual element is going to respond to forces. And so we can take, for instance, element 1, or actually this doesn't really matter. This is just generic element here. We can take some generic element and for that generic element, we're going to have a force that can act in the x direction on node I. And this will lead to a corresponding displacement of this node, which would be u x I. So this is the ith node. We can have, in general, we could allow there to be displacements in the y direction. So we could say that there's also a force y I that would lead to a displacement uy I. And if that's the ith node, then we can go over here to the j node and we can say, well, we have a force f xj, which would cause a displacement u xj, and similarly fyj, causing a displacement of u yj. And I should have probably labeled this as my ith node, this as my j node. And here we're talking about some generic, this is true in general for all of these. This is x bar e, y bar e. So this is just true in general, that at each node we have 2 degrees of freedom, so it can move in x and y. Therefore, you could have forces acting in x and y, and then this is all written and corresponding into the local coordinate system. Think back to springs just for a moment. This will be helpful for us. You know, if you think about a spring, oops. If you think about just a linear spring, and we take this and we stretch it out, due to the application of some force, then we know that there's going to be our corresponding. So let's say here we have some initial length between those 2 nodes of L. Then we'll have some kind of displacement here of D. Then our relationship here is that our spring stiffness, Ks, has what's referred to as an equivalent spring stiffness. Sorry, let me say this again. The stiffness of each member has an equivalent spring stiffness, Ks, that is written as EA over L. This is what's referred to as the equivalent So we're using what's referred to as a two-node bar, which is the element we're using. So the element is what's referred to as a two-node bar. Which is basically treated as a linear spring with a equivalent spring stiffness of EA over L. So that means the entries in our global stiffness matrix, that master stiffness matrix in purple on the screen there, the entries are going to have EA over L in there. And then there's going to be some way of kind of decomposing the force vectors depending on how the member is oriented relative to the forces being applied. But essentially, since we're just looking at springs that can only take axial loads, the stiffness or the response, the resistance to deformation is going to be dictated by how stiff those members are. So our stiffness matrix should have EA over L entering in the various coefficients in capital K there. Okay, we're talking about an individual member. And so for each individual member, since we have a force, 4 forces and 4 displacements, for each individual member, we can write down the member stiffness equations and the member stiffness matrix. So we have 4 force vectors, 4 displacement vectors. So we should be able to write that Fxi for the element and I'm writing this with a bar here to denote that this force is living in the local coordinate system. There'll be an Fyi, there'll be an Fxj, and an Fyj. That'll be equal to, let me just move that down. That'll be equal to member stiffness matrix. I'm going to write this one out, I think, just so that you can see it. This one's kind of important, which will be K in the local coordinate system for each element. This one is Xi, Xi, K, Yi, Xi, K, Xj, Xi, and Kyj, Xi. And we can keep going, K, Xi, Yi, K, Xi, Xj, and Xi, Yj. And so you can kind of imagine going through this yourself, Yi, Yi, xj, xj, yj, yj. I'll just finish writing this out here, just so we have it.
Hey, Professor.
Yes.
So this matrix is symmetric, right? So the yixj is the same as the xi yj.
Yes.
Yeah, it's symmetric. Okay.
Yep.
Okay.
I probably should have saved myself some time by writing it out that way. And this is going to multiply our nodal displacements. So u, y, I, da, da, da. And so what we have here is so this is what's referred to as our member stiffness equations. We can write these for each individual member in their local coordinate systems. Okay. Questions so far? Let me just zoom back out and tell you what we're trying to do. We really, if we can just solve F equals KU for the entire structure, then our problem is done. We typically either know F and are solving for U, or we know U and we're solving for F. But before we can do that, we need to construct the stiffness matrix K, which is going to be dependent on the particular structure you have. So how are all the members oriented and connected together? What are the entries of that stiffness matrix? Once we have the entries of that stiffness matrix, in principle, we can solve F equals KU. So what we're going to do is we're going to solve for the stiffness matrix of each individual element or each individual member in their local coordinate system. And then take that stiffness matrix in the local coordinate system for each element and transform it into the coordinate system of the global structure, and then insert those components now that are written in the global coordinates into the big stiffness matrix K. That's the idea. That's what we're trying to do. We're trying to use the local stiffness matrix of each member, because that's very simple to figure out, convert it to something that is in the global coordinate system, and then put it inside of the big K global stiffness, master stiffness matrix. Once we have the master stiffness matrix, we can solve the problem. Questions?
Hey, Professor.
Yep.
So how do you solve for the local stiffness matrix if you don't know the forces and displacements?
Great question. That's what we're going to do right now.
Okay.
Because the way you typically do this is you usually know something about how these elements that you've chosen, in this case we chose a 2-node bar, how we know how a 2-node bar deforms in response to forces. And so for a 2-node bar can only carry these axial loads, right? So we kind of know that looking at our generic member, looking at this thing here, this structure can withstand loads from xi and xj. It cannot withstand loads in fyi or yj. And so we can use that to figure out what the, and that's just based on our understanding of springs. When we think about a simple spring can be loaded this way, and that's all. Can't bend, can't shear, can't twist. A spring can just be stretched or compressed in 1D. So what does that mean? That means we can come back and think about, okay, what are the forces in this system? So for instance, we know that for a linear spring, we know that we can relate F to the displacement through some stiffness. Now we already know that our stiffness can be written in terms of the effective or equivalent spring stiffness, EA over L. Now this structure can only withstand forces in the x direction. And we know that for this structure to be in equilibrium, if there's only forces in the x direction, then those forces have to be equal and opposite to each other. So for instance, F of xj is positive. So here, F of xj is pointing in the positive direction, so that one's positive. F of xi, in order for this thing to be in equilibrium, has to be negative, kind of as we've drawn here. And so we would say and we know that our displacement is going to be the difference between the nodal displacement of the j direction, which is moving positive in the way we've drawn it here, and we'll take away any displacement of node I in that direction. And really, what I've written right now, what I've written right here, is the the solution, or this is the member stiffness equation for a 2-node bar, right? It's that the force in the X has to, xj, the force at node xj has to be equal and opposite to the force at node xi. And the displacement is going to be the difference in terms of how much node j moves in the x direction minus how much node I moves in the x direction. And the relationship between those forces and those displacements is dictated by how stiff the spring is, which is going to be written as EA over L here. So in a lot of ways, that's the kind of the end here, but we're really working with matrix methods. We're working with writing these equations that I've just written out kind of informally in terms of a matrix formulation. And so what that means is that we can write that our force vector, actually, I'll just save myself some time here. So to write what I just wrote, as a set of matrix equations, we would just simply write, oops, that we're going to have the generic elements modulus area and length multiplying a 4x4 matrix, and just translating this equation into matrix equations means that the entries of our stiffness matrix for this member are simply 1, 0, -1, 0, 0, oops, 0, 0, 0, 0, -1, 0, 1, 0, 0, 0, 0, 0. If you haven't worked with matrix equations in a while, just do yourself a quick check to recall that what we're saying here is that there can be no forces in the Y. So for instance, these all have to be 0. These all have to be 0. The force in the X can only cause displacements in X. So what we're saying is that this force here can only be affected, can only cause displacements in X. Same for this force here. And that's why these entries appear as non-zero in the matrix. The negative sign.
With EA and L square.
Sorry, what was that?
The K is a square, E is a square. The K of the matrix in front of the matrix, the EA over L. Are all these?
Sorry, let me be more clear here. Those are just saying that each element.
Oh yeah, I get it, but I didn't see.
Sorry, I'll make that more clear. I wrote that really messy. Each element might have its own length, area, or elastic modulus. This here is the elemental stiffness matrix in its local coordinates. So this is true for every element that I drew here. This equation, as written, is true for every element here. So we're done. This is true for every 2-node bar. you can write down the stiffness matrix of a generic element in its local coordinate system, and that'll apply for every member of the structure. And then our goal is we want to convert this stiffness matrix for each element into the stiffness matrix for each element in the global coordinates. So this is in local, and we want to convert this to global. And then we can we're going to add the stiffness of each element into the big K, the master stiffness matrix, which is our way of getting, basically conceptually taking how stiff each element is of the structure and helping to construct the overall structure so that you have some sort of global stiffness matrix defining how rigid or how much that structure resists deformation. So we're kind of, at this point, we're done. And the next step is to go between the local and the global coordinates. Questions?
I have a question, but I don't know if it's like a smart question or not. The thing is, I was questioning myself, what is the logic behind putting all the parameters in the matrix to 0 and not the forces and displacements? I mean, why shouldn't we tell that the displacement in the y direction and the forces in the y direction are 0? Instead, we're setting the parameters inside the matrix to 0.
Basically because we end up constructing a global stiffness matrix. And when we reassemble the structure, we want to say that there are going to be some unknown displacement. So let's pretend we're applying forces to a structure. So we know F, we're solving for U. We want to leave U be a generic set of unknowns. As you go back to this part of the equation here, we want to leave U as generic unknowns that we're going to solve for in our problem. And what's going to happen is, in order to do this, in order to reassemble the structure, we're going to have to go back and say, hey, look, we blew this thing apart, but this node and the way it moves in X and Y is actually the same as this node and the way it moves in F and Y, in X and Y. And so even though we solved for these the stiffness of member 2 and the stiffness of member 3 independently, we're going to use our knowledge of how the structure is put together to constrain the nodal motions of, say, in the y direction of node 2, that whatever that is for element 2 has to be the same nodal displacement for node 2 of the third member in that direction. They have to go together. And so what we want to do is we want to leave the forces and the displacements as the kind of the state variables in the problem. The displacements will be our state variables that we're solving for, and we're going to apply some forces. And we just want to ensure that those forces don't cause not allowable displacements. Does that make sense?
Yes, from what I understood, it's like in my local coordinate system, the displacement might be 0, but then when I move to the global one, it might not. So I have to not put it to 0.
Exactly, because you might have this member trying to actually push it this way in response to that force, whereas this one, actually a better way would be this one in response to an X force is going to have some Y component, whereas perhaps, or X component, I had it right the first time. Let's try it again. So your diagonal truss in response to a force this way, or sorry, in response to a force this way, will have some X displacement, which means this node in response to a force this way will have some X displacement because of this connection here. So it's not that this node has 0 displacement in the X direction. It's that as it's loaded, there's no translation of this force can cause any X displacement of this node.
Okay,
But because it's connected, it's not actually 0.
I got it. Thank you.
Okay. Well, I think what I will do is stop here for today, and we'll pick this up again next Tuesday. And this is where we're going to leave off is, and where we'll start next Tuesday is on how to take this in the local coordinates and turn it into K in the global coordinates. So I'm going to stop a little bit early today, and if you have any questions, let's chat about it now. But this seems like a decent stopping point.